What is it? Okay. I would like to continue with some kind of geometric features that can be created by the computer-aided design software. So for example, the non-uniform rational B-spline, or we can the NURBS surfaces, are widely used to describe feature and curve in CAD, computer-aided engineering, and computer-aided manufacturing software. The standard CAD file like the initial graphic exchange specification and step file stand for the standard for the exchange of product model data are commonly used in order to exchange information between different kinds of software. Yes. And generally speaking, the step file does not contain the history of the work, and therefore you can protect the content of your work. Just show how the model looks like, and it's okay. The new additive manufacturing file are being proposed and developed by the yeah, International Standard Organization and American Society of Mechanical Engineering and other organizations. New file formats are being designed for use with the additive manufacturing, and therefore they would like to overcome the limitation of the STL and the additive manufacturing files with improving the functionality and streamlines process of design to 3D printing and so on. 3D printing or can use the 3D scanning, 3D scanned part. Yeah, this is somehow related to the reverse engineering process. When we, as already mentioned, you can create model, the physical model first, but it's not made of the same material that you expect. It can make of, for example, clay, just to for creating the, the geometric features of the part, and we scan to capture the geometric feature of the part, and that's all. And afterward, we print out with the material that we plan. And we use the 3D scanning in order to create a point cloud of data in a coordinate system. We need to smooth the data after importing the or after using the cloud, the point clouds. I'm sorry, this is to create the point cloud. It's not the cloud that mây. It's not code. And to smooth, to create the point cloud of data, and then you use the algorithm in order to smooth the data and to create the surface model. They aim at these aim at building up the approximate surface representation of the solid model, and then you export the STL file, and then you use the suitable software like, for example, Autodesk Fab in order to slice the STL model and to perform some kind of setups before subject the model to the 3D printing process. And on the right side, you can see that there are several models, and we have some kind of grid, or the lattice, yeah, where we can move the point, and then the surface will be modified accordingly. Yeah, this is somehow called it freeform modeling. Yeah, where you can modify the surface based on changing the position of these points, deep points. Yeah. Computer-aided engineering Is a process of performing engineering analysis using the software for simulation, prediction, and optimizations. And normally we can perform different kind of analysis. So for example, analysis, thermomechanical analysis. So combinations, we consider the two factors, both mechanical factors and thermal factor at the same time. So we have thermomechanical analysis, fluid dynamic effects, and so on. And for the moment, there's many things that can apply the computer-aided engineering in order to perform the simulation, the relating simulations. Yeah. In the field that we are interested in, I mean additive manufacturing, uh, the interests are placed on heat flow analysis because it affects the quality of the material after the sintering or melting process. The stress analysis because we know we heat up the materials to the molten state, and we have the thermal gradient inside the pot during the additively manufacturing phase, and therefore we have the residual stress, yeah, coming from the thermal or mechanical forces in order to predict the performance of the design part. Model-based engineering, we have a wide range of analysis that can be used to understand the thermal, mechanical, fluid flow conditions. They must to see the result of the prediction first, and if necessary, we can change some feature of design in order to optimize performance of the part. That's what we. That's what many engineers or researchers are doing at the moment, model-based engineering, in order to modify the design or optimize the design. Yeah, both in terms of the performance, the weight, and to improve the energies, the fuel consumption efficiency, for example. Finite element analysis. Yeah. So I think that you might be familiar with using a certain kind of software, like for example Abacus, in order to perform some kind of analysis. It's simply starting with the construction of the CAD model, and then you export the CAD model, import into the FEA package software, and then you need to create a mesh. You need to assign the materials. You apply both the boundary conditions. Yes, so different kind of constraint. Defining the regime, either this is linear elastic analysis, nonlinear analysis, materials, fixation, and so on, before we can perform or simulate the behavior of the system as a function of time. And to predict, so for example, the principal stress, the maximum vorticix stress, so for example, or the equivalent stress. We could predict the deformation, strain, and so on. Yeah. So on the right side, for example, you could see the structure optimization performed by uh, Solid Thinking Inspire. So it's one of the software developed by the OnTair company. So initially, we need to define the unmodified regions. So the region that will not be modified during the optimization process, and the others region of the part that will be modified during the structural optimization process, assigning with material, defining the external forces or the other, let's say, factor, the boundary condition, the fixations, the reason for the analysis, and then run. And after the running process, we have the optimized model. So the volume the material within the design area will be modified accordingly based on the condition that we have set up. And then we have the optimize. And after we have the optimized model, it's necessary to translate into the, how can I say, the smoother model. Yes, the smoother model. Of course, to reduce the stress concentration and to make it more reasonable to be printed out. Yeah, of course. This is a matter of aesthetic design to make it more attractive to your customer, of course. And that's why you have the translation from the so-called as optimized model to the ready to be print model. Yeah. Computer aided engineering. Yeah. So we continue to consider this field. So the FE analysis of the additive process is really a challenge. So it's the physical consideration rather than uh, is the matter of physics. Yeah. It's challenge because if you want to improve the additive process, yeah, you need to investigate different kinds of parameters associated with the additive manufacturing. To do that, you need to consider several challenges in terms of the mass refinement. It's also a challenge. Yeah. For modeling, moving heat source and powder interactions. So on uh, the last slide of the third chapter, you see that how complex the process, the interaction between the heat source and the powders and the material in general, how complex the process is. And therefore now we need to mesh, to refine the mesh in order to investigate the moving heat source and the powder interacting with others, with each others, is quite difficult. Just the small side of the pole, because we have the, how can I say, the focus of the energy beam, and therefore we at the at a certain period of time we just have a small pole. We have high speeds regarding the building process. Needless to say, we have limited data, or we have limitation about the knowledge of material property data. So uh, for those material supplier, they develop the material and they have the data. But generally speaking, they will not publish all of the data regarding the material that they are developing. You know, just some, but not all. And you know that when you define the material which is assigned to your motor, you need a lot of information. Not only the hinge strength, the ultimate tensile strength, but others, like for example, fatigue properties of the materials. You know that? And if this information is lacked and is limit the accuracy of the simulation process and affecting the predicted result. And last but not least is the interaction of many additive manufacturing parameters, because basically when we investigate an influence of parameters on the additive manufacturing process, we tend to keep the other parameters constant. We modify one parameters and let the parameters have several values and investigate the influence of changing values of these parameters on, for example, finer properties of the materials. But now, if you have the interaction of many additive manufacture, many parameters of additive manufacturing process, and then here this is really a big challenge, yeah, to be considered during the simulation process, and therefore is under development. An application of the computer-aided engineering used for AM is topology optimizations. So topology optimization is, it can be the FE analysis process. Yeah, because practically it's based on the FE analysis. Yeah, it's based on the FE analysis. You also need to define the material. You also need to match the model. You need to define the the regime for the analysis. Yes, uh, need to define the boundary constraint, yeah, fixation, and so on. Yeah. But then there is correlation, or there are correlation between the material density and the stress inside the region that the regions that are subjected to be modified. So instead of showing the stress, so for example, distributed within the design volume, let's say, it will show you uh, the density value. Yeah, the density values for each element, for each element. And by defining a critical value of material density, and the software which can be used to run the optimization, I mean topology optimization, will eliminate those elements which have the virtual density smaller than the critical values that you have just defined. And for those with the density being larger than the critical value which you have defined, and then it convert into the solid elements, and the other will be free volume. And then you perform the topology optimization, meaning that you erase or you eliminate the unnecessary material within the design space of the part. Yes. And after this process, I would generally say that we have the part has the new part or the optimized part has comparable or even better performance than the original structures, and simultaneously is lighter than the original structures. Is that the point? That's the point. And it's actually performed through the iteration or the iterative optimization, trải qua một vài cái vòng lặp, đúng không ạ? To build the lightweight design. The additive manufacturing can benefit from the topology optimization in terms of the ability to create complex design for the fabrication. So people say that is the naturally match between the topology optimization and the additive manufacturing, because the topology optimized part is too complex to be fabricated by the traditional manufacturing process, like lathe cutting, like even casting, like forging, like drilling, and so on. But uh, additive manufacturing can. Yeah. And at the same time, we can save material because additive manufacturing can fabricate the near net shape component. Yeah. So it's match. So the additive manufacturing can benefit from topology optimizations. And there are several kinds of software that can be used for running the topology optimization, like, for example, anti-hyperworks OptiStructs, or simply called OptiStructs. Solid thinking inspired. Yeah, even Unzip. Yeah, Unzip can. I do not know about Upcurse. Yeah, right. The 3D modeling software like Autodesk Inventor can perform the topology optimization. Siemens NX, I think it can. And now there are many actually software, commercial software actually uh, can be employed for running the topology optimization to create the optimized structures, having better and even lighter than the original parts. However, this topology optimization is not an universal method, uh, and it is also contained some kind of limitation because the computer optimized design. Uh, and during actually the optimization process, the software or the algorithm does not contain do not consider the critical flow size, the surface finish condition, and so on. This is also under development as well. Oh, come on. Sorry for a minute because I need to close the door. Yeah, okay, that's fine for the moment. So where is it? Let me see whether I'm showing you the slide or not. Yeah, here. Okay, so where am I? Here. So on the right side, you could see a sick figure or a sick part of a figure showing you the process of running topology optimizations. So initially, you have the original model, and you can define which area those will be preserved, those will not be changed or will be modified during the topology optimization process. And then in the third step, you will need to define the whole new model. Uh, this whole this new model contain the features called the preserved features, or the features those are similar to those belong to the model one, let's say, like the hole, for insert pin, for example, the hole for insert pin, and the other hole, and the area that we need to apply the fixation, the areas that we need to apply the fixations. For the other in brown color, we call the design volumes. So the design volume will be modified during the run of topology optimizations. So just the brown, yes. The red brown color actually, red brown, not actually brown. And after the run, you will have the optimized model in the part 4 of the figure. Is represented in terms of the yellow, and the other color represent probably the fixation and the preserved volumes. Preserved volumes. And once you have the optimized model, this is necessary to analyze the model by the FE's package software in order to see the stress, the strain distributed within the model when it's subjected to uh, the virtual loading condition, to see how it deform What about the maximum stress, vormicid stress present on the structures, whether it is above yield strength or below, and so on. Even the fatigue analysis you can perform with the part 4 in the fifth step. And if everything is okay with the virtual check, and then you can somehow modify a little bit to make the model 5, which is a little bit more attractive, and you obtain the model in the step 6 that are somehow looks great, and it can virtually it can withstand the given forces or the given within a given conditions. And then I would say that it can be printed out after setuping in the preparation software. So for example, orientation with respect to the building plate, generate the support structure, assign material, defining different parameters associated with additive manufacturing process before printing out the model. So the 6th step show you the flow of the optimization process. In that case is the topology optimization to prepare a model for the 3D printing process and to optimize the structure of the part so that it has compatible or better performance. The part, the optimized parts with respect to the part 1, let's say. So compatible or better performance, and at the same time it's lighter because we already eliminate a certain amount of material from the part. Yeah, and that's the reason that we run the topology optimization. Tôi nghĩ là nên nói thêm với các em một chút bằng tiếng Việt là về cái nguyên lý của cái anh topology optimization ấy, thì về cơ bản thì nó cũng là chạy các phương pháp phân tử hữu hạn dùng để phân tích thôi. Về cơ bản thì vẫn là phân tích để tiên lượng cái trạng thái ứng suất, đúng không ạ? Xem là ứng suất vormicid cao nhất đó là bao nhiêu, đúng không ạ? Tìm predict về cái độ biến dạng, vân vân. Yeah. Thế thì trong cái quá trình analysis đó thì rõ ràng là chúng ta phải có cái quá trình match, đúng không ạ? Và các cái kết quả thì nó sẽ được đưa về các cái phân tố, đúng không ạ? Thế thì ở đây sau khi cái quá trình FE analysis và cái quá trình topology optimization nó có một cái sự gắn kết với nhau, bởi vì nó sẽ dùng một cái thuật toán, phần nhiều thì người ta dùng thuật toán là SIM, có nghĩa là Solid Isotropic Material with Penalization. Thì các em có thể tìm hiểu thêm về cái SIM, Solid Isotropic SE Material MP, SEMP, SIM. Thì đấy là một trong những cái thuật toán mà giáo sư Ben Dozer của Đại học Technical University of Denmark propose, nếu tôi nhớ không nhầm, SIM. Thì cái thuật toán đấy sẽ đưa từ nó sẽ tạo ra một cái mối liên quan giữa cái ứng suất mà cái software nó predict được, đúng không ạ? Và nó chuyển gắn với cái relative density của cái element đó, có nghĩa là cái ứng suất nó là bao nhiêu thì nó sẽ tương ứng với một cái giá trị nhất định với cái density. Cái density tôi gọi là cái mật độ của cái element. Mật độ ở đây bằng 1 thì nó là vật liệu đặc, 100% là vật liệu đặc, và bằng 0 có nghĩa là free volume, có nghĩa là rỗng luôn. Và ở giữa thì nó là intermediate density elements, có nghĩa là có cái mật độ trung gian. Thì thực tế ra vật liệu thì chỉ có hoặc là đặc thôi, hoặc là rỗng, đúng không ạ? Không có cái gọi là vật liệu trung gian đâu. Đấy, nhưng mà cái algorithm hay có cái thuật toán đấy thì tạm thời nó cứ chia nó là hoặc là đặc, hoặc là rỗng, hoặc là có cái giá trị trung gian. Thế sau khi nó đã đưa được về cái giá trị đấy rồi thì cái thuật toán đấy tiếp tục giải quyết cái bài toán là define đến một cái giá trị critical value của cái density đó. Tôi lấy ví dụ là 0,7 chẳng hạn, có nghĩa là 70% relative density, đúng không ạ? Có 30% là chứa các cái free volume rồi. Thế khi mà define cái relative density, cái chỉ số critical đó, thì tất cả những cái elements nào mà lúc nãy tính ra có cái relative density lớn hoặc bằng 0,7 thì thuật toán đấy nó convert hết về 1. Có nghĩa là gì? Là tất cả những cái element nào có relative density 0,7 thì nó đưa về hết đấy là những cái element có cái mật độ là đặc tuyệt đối, có nghĩa là hoàn toàn là đặc. Còn những cái element nào mà có cái chỉ số density nhỏ hơn 0,7, tôi lấy ví dụ thế, thì nó quy hết lại về thành cái vật liệu rỗng đó. Và cái bước đó làm xong thì chúng ta nhận được một cái chi tiết làm thành bởi rất nhiều cái elements có cái chỉ số density làm tròn từ 0,7 và nó đưa hết về 1. Thì đấy là cái optimized structure của chúng ta. Thế nhưng mà nó thể hiện bởi bằng cái elements, cho nên là rõ ràng sau cái quá trình mà chúng ta optimize xong thì tôi phải smooth cái surface để loại bỏ các góc cạnh của cái elements này nó đi, đúng không ạ? Thì trong cái Ontae OptiStruct chẳng hạn là có một cái câu lệnh OS smooth để nó smooth, nhưng mà thường nó chạy chả ra cái gì cả. Đối với những chi tiết phức tạp chạy thì đúng là không ra thì là không có kết quả. Thì tại cái thời điểm mà tôi hay dùng software đấy thì tôi thấy rằng là nó phụ thuộc rất là nhiều vào người dùng, rất là nhiều người dùng. Mức độ tự động của nó ở cái bước smooth là không cao. Bây giờ thì không biết thế nào, chắc là nó phải hơn rồi. Đó. Thì những cái vật liệu mà có cái thuộc những cái vùng mà có trạng thái ứng suất nó thấp, đúng không ạ, thì vốn dĩ nó chịu lực không cao, thì đương nhiên là software nó sẽ loại bỏ những cái vùng vật liệu đó, đúng không ạ, để làm cho chi tiết nó nhẹ hơn trong khi vẫn đảm bảo cái điều kiện làm việc của chi tiết. Thậm chí trong một số trường hợp nó còn add thêm vật liệu một ít thôi, nhưng mà nó vẫn giúp cho gia cường cho cái kết cấu của chúng ta và làm cho cái độ cứng hay cái khả năng làm việc nó còn cao hơn. Thì trong những cái tình huống đó, đúng không ạ, trong những cái tình huống đó thì chúng ta đạt được toàn bộ các cái tiêu chí cả về cái giảm khối lượng cũng như đảm bảo cái performance của cái chi tiết hoặc là nâng cao performance của chi tiết. Thì đấy là một đôi lời tôi muốn nói thêm một chút về cái anh topology optimization để cho nó clear hơn một chút với các bạn. Và đại đa phần bây giờ để mà nói thì người ta dùng topology optimization này, dùng lattice optimization này để tối ưu hóa cấu trúc cho chi tiết, để nâng cao cái khả năng làm việc, làm nhẹ chi tiết đi, đúng không ạ? Và những chi tiết sau cái quá trình tối ưu hóa đấy thì nó extremely match với cả cái anh additive manufacturing. Một cái mục nữa của chương số 4. Yes. The next topic that we like to focus on within the chapter 4 is computer-aided manufacturing. CAM. Yeah. CAM take the CAD file to create the instruction for the CNC system to fabricate the component. And sometimes you have to, let's say, code in order to provide some kind of command to guide the CNC machine for fabricating the part. I'm not so familiar with coding for CNC actually. The CAM software platform generates the tool paths for lathe milling machines, laser cutters, and others. So it's just the system that contains a lot of type of machine tool that can be used, yes, with the high degree of automation in order to cut the parts, and therefore we can improve the productivities of fabricating components. We know that with the higher accuracies because it's controlled by software. It's controlled by software. The CAM files can preserve parametric relationship with the original file. So you can easily scale, change the dimensions, or it means that you can easily modify design, the first design. The CAM file contains the M code, G code, and whatever you call. This means that is more complex and less automated than creating the SDL for AM. So the SDL, the SDL is sequence or generations for AM is highly automatic. Yes, and just even you use the inventor, for example, you just say convert. Yes, use the command convert to the SDL or export in terms of the SDL file. And that's all. You have the SDL file that can be imported into the software of the AM machines. That's all. It's, however, in the case of a CNC, you have to program, yes, and code G codes. The CAM can also refer to the process of slicing the SDL file and translating to the 3D printers. Yes, because for some 3D printers like direct energy deposition, and you have to also control the robotic arms. Yes, control the robotic arms. And generally speaking, yeah, you have the design process, you have the verification process, and everything is okay, and then you slide the motor, print out, and then finish. And within the design step, you can start with creating the part by using the computer-aided design or computer-aided engineering software. With the computer-aided design, you can start with the sketch, yes, and then you create 3D part. With the computer-aided engineering, you can start with how can I say, scanning the motor, create the STL, or you can directly run the topology optimization for the motor, and then you have the optimized parts. This is also the design. You can also run different kind of structural optimization like topology optimization or lattice optimization. This is done by the computer-aided engineering software. Yeah, computer-aided engineering software. Verification is mean that, okay, you have the design, but you need to be sure that this design can work appropriately in a given conditions. So you put in the design to the computer-aided engineering software like Abacus, like ANSYS. Yes, you check virtually to see, how can I say, distribution of stress, the strain. And you can also use the predicted stress and strain as the input data for fatigue analysis. So how many cycles that the part can withstand before the initial crack occur on the most critical surface of the materials. Slicing, okay, it means that when the motor is verified, it means that, okay, it can virtually work, and then you slice to prepare the motor for the 3D printing. Yes, printing parameter need to be set up. The G code generation, especially for the direct energy deposition, because you need to control the robotic arm, the robotic arms. The material selection for sure, and then you need to deposit the material layer by layer until the 3D physical part is completed or is formed. And finally, for server additive manufacturing processes, you need to perform the post-processing step. For example, to remove the support structure, to remove the residual powders inside the internal volume of the part. Yes, you can perform some kind of enhancing the qualities of the surface materials of the surface. Because why? Because the surface roughness of the part after the 3D printing is not so good comparing to those parts which are made of traditional manufacturing. And therefore, if you want to have the part with attractive appearance, with very smooth surface, and then you need to apply the post-processing step like milling. And you may need to apply some kind of thermal treatment to modify the properties toward the properties enhancement or improvement. Yeah. Then there is a video clip. There are two video clips actually showing you the process, but then you can do it at home. Now you are at home, but not at this time. Yeah. Just to save time. Just to save time. And this figure is taken from the was taken from the MPDI journal. Yeah. And there are several computer-aided manufacturing software. So I would say engineering actually, or maybe aided manufacturing that can be used for different phases during the design process, during the topology optimization, massing, process simulation. Oh, process simulation, in-service simulation, and pre-printing slicing. So design is this commonly used. SolidWorks, CATIA Inventor are commonly used, and X created by Z-Man. Yeah, 3D Max, Autodesk, UDS Max, Autodesk, Blender. I haven't used Evolve. Evolve, as I remember, is developed by the Ontaire. Rhinoceros, yeah, but I haven't used. I don't know about Rhinoceros, but it's quite it's also famous software to deal with the 3D modeling. Topology optimization, yeah, solid thinking inspire is quite powerful. Dassault similar abacus, yeah, Dassault system. Autodesk Fusion 360, yeah, I would say that for the moment, Autodesk Fusion 360 have already embedded the so-called uh, generative design. Is somehow a topology optimization, but they combine with the use of artificial intelligence. So by using the topology optimization, you perform one run, you have one result. Depending on you the how can I say the critical density that you have selected. So you have one result only for your selection and for your run. But with Autodesk Fusion 360, yeah, with the similar definition of the model that can be subjected to the topology optimization, for example, and with the artificial intelligence, the software can point out multiple results for multiple materials at the same time. But if you want to modify the model after the topology optimization, so it's not easy with Autodesk Fusion 360, because at the moment is the STL file and the modification is in general hard to perform. Yeah, 3D mesh, work with mesh and topologies. So material matic, 3matic is famous. Autodesk NetFab is also famous software in order to somehow modify the 3D mesh. So it's not just like the meshing process in Abacus or in ANSYS, but now you need to perform some kind of modification with the mesh. So if the error occur and you need to fix the error, and then you need the support of Inspire, Materialize, the Autodesk NetFab. That's what I mentioned. It's not the normal meshing process that you do with, for example, Abacus. It's different. It's the modification. So, for example, if you want to add several elements to a certain position, yes, just manually add, yeah. So you can do it with Materialize schematic, not with Abacus, because you have model, you set up the regime, and the software will help you to mesh the model completely, the whole model, and not yes. and at least a certain reason and more. But if you need to add individual mass, so I don't think that you can do it with abacus or anti. In this case, you need to have the software having this function, in order to, how can I say, to play with the mass process simulation. Yeah. It's actually the physical simulation. So, but we are somehow familiar with in-service simulation. Yeah, in-service simulations. So to simulate the working condition of the part, to see how the part perform, and how the stress distribute within the part in a given condition, and we use let's say hyperworks, anti-hyperworks, our curves. Yeah. This one is Nastran or Pastran. I do not know about Pastran. Inspire and it comes from ontology, so on. And okay, and last but not least, we pay attention to the two most powerful software that is to prepare the pre-printing slicing, netfab, and materialize magic. Autodesk Mass Mixer is okay, but it's free for the Autodesk Mass Mixer, but it's used to prepare the model for uh, printing out the polymeric material, not for preparation for for the print with metallic materials. We have the last slides of chapter 4 before we commence with the chapter 5. I think we can stop for 10 minutes and then we will continue up 2.